we learned about the different kinds of intermolecular forces, right? And now we're going to look at some of these state changes. The first one we're going to look at is vaporization. So vaporization is the transition from a liquid to a gas. And it does not have to be when the liquid's boiling, right? Because water evaporates at room temperature. It's a good thing, otherwise everything would always be wet, right? So how does this happen? So here we have our beaker of water with our little Mickey Mouse water molecules, and they're like swimming around, right? They're in constant motion. Here in this open beaker, some of the ones at the surface can have enough energy to escape and get into the gas state. And when they get into the gas state, they go in straight lines until they bump into something. And since this container is open, most of them are just going to go out into the universe, right? But you can also have some that might come back and land in the water and get stuck again. So this is where that quote at the beginning of the chapter comes in. It's a wild dance floor there at the molecular level. So this is kind of like a mosh pit. Do people still do that? Yeah. So, this is like crazy, right? And some of the people in there aren't moving a lot, and some people are moving just way, way too much, right? And so some of them can escape. Most of them are just kind of stuck in here. So vaporization is going from a liquid to a gas, and the opposite is condensation, going from a gas to a liquid. And those are words that we use in everyday life. We talk about something evaporating, or there's water condensing, right? So the average energy of those particles will increase with temperature, but not all of the molecules are have the same energy. The temperature is the average. So at any given temperature, we've got a range of energies. So at low temperature, this might be sort of the average kinetic energy, but there's this big range that are of different energies that are possible. When we increase the temperature, we're going to increase the average amount of kinetic energy, but then this distribution also starts to flatten out. And so if this dotted line represents the minimum amount of kinetic energy needed to escape from the liquid, we can see that the area under these curves is going to show us how many molecules have enough energy to escape. So at a higher temperature, there's a lot more molecules that could possibly escape. They're only going to escape, though, if they happen to get close to the surface and are moving in the right direction. So at higher temperatures, vaporization occurs more quickly. Now, I'm going to go back to this one. I'm going to talk about the analogy I like for vaporization. Have you guys ever played Red Rover?
Yeah.
Red Rover, send Susie right over, right? And so you got two lines of kids holding hands, and then, somebody calls for Susie to come over, and so Susie runs across the grass, and she's trying to break through your hands, right? So this is why they don't allow this in school anymore, because somebody could get hurt, right? Kids like getting hurt. Well, yeah, and if you know these kids, you're like, oh, that one's a wimp. I'm going to go over there, and those guys they're never going to let go, so don't go there, right? Okay, so the surface of the water here. Remember we talked about surface tension, right? So the surface of the water is like the Red Rover line, and these guys are Sally trying to come over, right? Trying to break through. So if this molecule is going in the right direction, if Sally runs the other way, she's not going to break through the Red Rover line, right? You have to run to the line, and you have to have enough energy, right? The faster she runs, the more likely she'll get through. Or if she's a really big girl versus a little tiny girl, right? Because kinetic energy is 1/2 mv squared. So these guys, some of them are headed towards the surface, and if they have enough energy, they can break loose. If they don't have enough energy, they just kind of, well, like with the red rovers, like the hands don't part, and, well, no, you've got to stay over here. Any questions?
Doesn't that need a catalyst? Not necessary?
No,
Oh.
no catalyst, because these are always in motion, right? The only time when matter is actually still would be at 0 Kelvin, absolute zero, which, as far as I know, no one has achieved that cold of a temperature.
Cool.
So things are always moving, right? Just like, we talked about the solid, liquid, gas states of students. Right now you're in the solid state because you're all sitting down, right? And you're not moving relative to each other. But you're all moving a little bit. You just scratched your cheek, you're eating something, drinking something, everybody's breathing, yes, love that. So everybody's moving, right? Well, in the liquid water, the liquid state of students is like during lab when we're all milling about, right? And some people might be kind of standing still, working on something, and other people might be, I have to go get to my solution before it boils over, and so they're walking quickly across the room. So some of these are moving slowly and some of them are moving quickly. And if you have one that's fast and it goes in the right direction, it can break through and that will evaporate, right? So evaporation is going from the liquid state to the gas state. At a higher temperature, you have more of these particles that have enough energy to escape, and so they will escape faster. So things evaporate faster at higher temperatures. That's why we put our wet clothes in the dryer. And the dryer heats them because it makes it dry faster, makes the water evaporate faster. This crazy computer. So higher temperatures, vaporization occurs more quickly. Another way you can increase the rate of vaporization is to increase the surface area of the liquid. In order to break free, the molecules have to get to the surface, right? So if we have some water in a tall, skinny glass versus the same amount of water in a shallow dish, this one has more surface area, right? More molecules have access to the surface. And we talked about the surface tension, and the surface tension actually is fairly weak compared to the attractions within the body of the liquid. But the surface tension here, that depends on the strength of the intermolecular forces, right? So if we increase the surface area, now we have better access to the red rover line, and so more people can get out. Evaporation occurs more quickly. Does that make sense? I kind of muddled around in there for a while. Volatile, that's the word we learned back in chapter 6. We did an experiment where we found the molar mass of a volatile liquid. Right? That just means that it's a liquid that volatilizes or evaporates easily. And non-volatile means it doesn't vaporize easily. Well, what's easily, what's not easily? Well, those are relative, okay? Liquids that have stronger intermolecular forces are going to evaporate more slowly, because that's like the people at the red rover line here have a much better grip, right? And so it's harder to break free. So you've got the same kind of energy going on here, and when these people run at the line, fewer of them are going to get through because the people at the line are better at being the red rover line. That make sense? So strong intermolecular forces, it's harder for things to break free, and so it evaporates more slowly. So, and you could do this later if you want. You could put some water on one hand and put some acetone on the other, and the acetone feels much colder, and look, it's already evaporated, right? Why did that evaporate so quickly?
Liquid. Was
It-
volatile liquid?
It's a volatile liquid, but why is it? Because the intermolecular forces are weaker in acetone than in water. So stronger intermolecular forces evaporate more slowly. So let's think about, what if that beaker is insulated? So as the particles are evaporating, there's going to be a change in temperature of the water. Is it the fast particles or the slow particles that escape? It's the fast particles. And the temperature of the water is a measure of the average kinetic energy. So if all the particles with high kinetic energy are leaving, what happens to the average? It goes down, right? So in insulated beaker that's open and allows the water to evaporate, the temperature of that water will go down.
Like what we did Monday night with our practical, like practice. How like we heated it up, and I remember you were like titrate pretty quickly because remember titration solution was already a temperature of its own. So
Well,
it started cooling
that's a
down
little
necessarily.
that's a little different.
Oh.
That's a little different because we're talking about a chemical change there.
Mm-hmm.
Yeah.
Oh.
And this is just a physical change.
Gotcha.
Yeah. But there's definitely some commonalities in there, but we don't want to go there. No. So the molecules that evaporate are the ones with higher energy, leaving the ones with lower energy behind, and so the temperature of the water left behind is lower now. And so that tells us that vaporization is an endothermic process. And the other way you can remember that is, well, how would you get water to evaporate faster? Would you heat it up or would you cool it down? You'd put heat into it to get it to evaporate. So putting heat into it, it's an endothermic process. Because it's an endothermic process, when we get sweaty and the sweat evaporates, it's going to suck heat from our body to try to maintain the temperature of the sweat, right? So the sweat evaporates and we feel cooler because it was an endothermic process and it's absorbing energy as it evaporates. Does that make sense? So if evaporation is endothermic, then condensation is exothermic. And that's one that's harder to think about. So I think the best way to figure these out is, well, evaporation, if I put energy in, if I heat it up, it's going to go faster, right? Okay, so that is endothermic. Then the opposite process has to be exothermic. When a gas condenses, it releases a lot of energy. And that's not something that's really obvious. But if you've ever stuck your hand in hot steam, the steam is going to condense on your hand, and as it does, it releases a tremendous amount of energy, and you get a really nasty burn from steam. Much worse burn than if it was just dry air that was the same temperature. And this condensation evaporation thing has a lot to do with our climate and the temperature changes over the course of a day. So I pulled these numbers off the internet. This is from 1971 to 2000 in July, comparing Fresno and San Francisco. So the average high in Fresno, 96.6 degrees Fahrenheit, San Francisco, 68.2.
That must have been closer to
In
1971.
July. No, it's always cold like that in San Francisco.
No, I meant like in Fresno.
In Fresno.
In Fresno, well, 2000, that's 23 years ago still,
Oh.
right? Yeah. It's probably higher now. But the low in Fresno would be like maybe 66. I don't know how that happened.
I'm only living in San Francisco.
Well, there's good things and bad things about that. Been there, done that.
I've been there, done that. Is that where you're in Fresno now?
Kind of. And so the difference is 30 degrees from day to night. You're like, yeah, so? Sometimes it's 40 degrees. What of it, right? Well, San Francisco, 68, 54, a difference of less than 14 degrees over the course of a single day. Right? Why doesn't the temperature change?
Because they're by the water.
Because they're by the water. So San Francisco is surrounded by water on three sides, the ocean and the San Francisco Bay. And the water absorbs the energy as it evaporates. And then at night, when the air cools down, the water in the air condenses back into the bay and releases energy, and it moderates the temperature.
So what you're telling me is I need to move somewhere cold?
Pardon me?
What you're telling me is I need to move somewhere cold?
Well, I'm not saying you have to, but if you don't like the heat, then you should move somewhere colder. But, you know, no place is perfect. No place is perfect. So, I grew up in the Midwest, where in the summer it's really humid. Like the day we got married, it was 95 degrees and 95% humidity. It's like a sauna. Man, it was hot.
And was it just like lost for long?
Oh yeah. But see, we know these things, and also if you plan an event in the Midwest, it's going to rain that day.
Oh, okay.
So you don't have your wedding outside in a garden. That's idiot. You have it in the church with the air conditioning, right? That's what normal people do. But, you know, so it'd be 95 during the day, and it might cool down to 85 at night. Well, there's no ocean. Where's the water? It's in the air. The water in the air can moderate the temperature. And I think we're all familiar with it. There's always a week or two in the summer where it just doesn't seem to cool down at night, and we're just like, ew, this is just icky, gross. Well, if you pay attention to the humidity, it's not like 95%, but it's definitely higher at that time. And that's why it's just not cooling down like it does. You go somewhere like in Arizona in the desert where it's like super, super dry, like 10% humidity, and the temperature just goes up and down over the course of the day because there's nothing to moderate the temperature. So this is one of my favorite things, if you can't tell. Mm-hmm. Any questions? So there's energy involved in vaporization. So we can call that the heat of vaporization, or technically the enthalpy of vaporization. So that's delta H, that's an H, delta H, VAP. So that's the amount of heat needed to evaporate or vaporize 1 mole of liquid at its normal boiling point. So we can make a chemical equation here, liquid water going to water in the gas state, and we can put delta H out here, plus 40.7 kilojoules per mole, right? So this is just like those thermochemical equations that we were dealing with in chapter 7, that you all loved so much. So this is always positive. Vaporization is always an endothermic process. You have to put heat into it. It will depend a little bit on the temperature, and that's why it says at its normal boiling point. But it doesn't depend a lot. So if we look at water here, normal boiling point's 100 degrees Celsius. So at 100 degrees Celsius, the heat of vaporization is 40.7. But at 25 degrees Celsius, which is considered room temperature, it's 44. Little higher, but not much. Okay? When a substance condenses, that's the opposite reaction, right? It's going from a gas to a liquid. Delta H is the same number, but opposite in sign. Because evaporation is endothermic, condensation is exothermic. And so we can use this number as a conversion factor to figure out how much heat is involved when something evaporates. Let's do that. Calculate the amount of heat in kilojoules required to vaporize 2.58 kilograms of water at its boiling point. So they're only giving us one number, and they're asking for heat in kilojoules. And these end up being dimensional analysis problems. So I've got 2.58 kilograms of water, and I'm trying to get to kilojoules. There's missing information. We need to know how much energy it takes to vaporize water. They didn't give it to us in the problem, so we're going to go back to the table and look it up. So it's 40.7, or up here is bigger, 40.7 kilojoules per mole. So we're going to need that number. And that's the heat of vaporization. So that's how we can convert between moles and kilojoules. So if we knew how many moles of water we had, we could use that to convert to kilojoules. How can we get from kilograms of water to moles of water? How can we get from kilograms of water to moles of water?
Divide by moles, but change the kilograms to 10 to the 3 grams.
Yeah, we could do that. We need to convert to grams, right? And so we could either make that a separate conversion factor, or we could just write this as 2.58 times 10 to the 3 grams. And then can we convert from grams to moles? Molar mass, right? Is this kind of coming back a little bit? We can't just forget, we have to hold on to all of this until the end of the class, okay? I know it's slippery, but just try. So 2.58 times 10 to the 3rd grams. So I want to convert this to moles of water. So I'm going to divide by grams of water. So the units cancel out. And then I'm going to multiply by kilojoules and divide by moles. The heat of vaporization is the relationship between energy and moles. So 40.7 kilojoules for every 1 mole of water. And then we can calculate the molar mass of water. So that's one I just remember. So 2.58 times 10 to the 3rd divided by 18.016 times 40.7. So that's going to give us 5828.48579 kilojoules, which is a ridiculous number of sig figs, right? How many sig figs should we have? 3. I'm rounding in the tens place, so we need to be careful, because sometimes students will take 5,828 and they'll round this to 583. 500 and 5,000 are not the same, right? You would have to put a 0 in there to hold the decimal place. Better thing to do is put it in scientific notation first. So I'm moving this 1, 2, 3 places. So 5.8, I want to keep the 2, but the next digit's higher, so I have to round up to 3 times 10 to the, I move the decimal point 3 places. Is 5,000 a big number or a small number? It's a big number. How do I feel about big paychecks? I feel positive, right? So my exponent needs to be positive, and there's my kilojoules. Any questions? I think maybe most of you see by now that over the course of the semester, we've seen like so many different kinds of problems that we can use this same approach on, right? We're going to look at what unit am I given, what unit do I need to find, and then how can I get from one to the other. Sometimes you have to use an equation in there as well. Sometimes you can just do it with dimensional analysis. But stoichiometry problems, titration problems, like the one for the lab practical, it's really just dimensional analysis. Okay, so we were talking about a sealed container. What if the container, we talked about an open container. What if it's sealed? So here we have an Erlenmeyer flask with a rubber stopper in it. And so we've got this mosh pit of water molecules, and some of them have enough energy to evaporate. And so they get up here, and they start doing what gas molecules do, and they zing around. They go in straight lines till they hit things. But now they can't leave the flask. So eventually, they're going to run into the surface and get stuck, right? So the rate of evaporation is going to depend on the surface area of the water, it's going to depend on the temperature, and it will also depend on the strength of the intermolecular forces. But here, the temperature is the same. We're not changing the temperature. The surface area is not changing. The substance is staying the same, so that's not changing either. So here we have a rate of evaporation. That rate of evaporation is going to stay the same. But the opposite process, condensation, initially we have no condensation because there's nothing up here to condense, right? There are no gas molecules here to condense. As evaporation proceeds and we get gas molecules up here, now condensation can occur. The condensation
You missed the other one.
Did I?
6:35.
6:35, thank you. It's just,
The other one was quieter, but you heard
Okay.
it, but this one was just obnoxious and loud.
yeah. So the rate of condensation is going to depend on how many gas molecules are up here, right? And so as evaporation occurs, we're going to get more and more gas particles, and so the rate of condensation is going to increase until we get to the point where the rate of evaporation and the rate of condensation are the same.
Can we say something similar for like champagne? Like when it popped the cork in and is that like the gas molecules finally escaping after being like vaporized in that bottle or something?
Yeah, so when you pop the cork on a bottle of champagne, the reason the champagne is fizzy is because it has gas dissolved in it. I believe that's carbon dioxide as well, just like soda, right? And they have to have that little wire cage on the cork to keep the cork from just popping out by itself, right? And so there's a lot of pressure in that headspace. And so you've got, actually we'll talk about that. It's slightly different. We're going to talk about that in a few minutes. Yeah. So we're starting out here. We've got water evaporating, but nothing is condensing. The rate of evaporation stays the same as we go along because it depends on the surface area and the temperature, and those things are not changing. The rate of condensation depends on how many gas particles are up here. The more gas particles that are up there, the more of them will end up landing in the water, right? These guys are zinging around. If I have one molecule up here, condensation is going to be very slow. If I have 5 million particles up here, I'm going to have a lot more condensation, right? But we're going to get to a point, and that's called a dynamic equilibrium, where the rate of evaporation is equal to the rate of condensation. And at that point, the amount of gas is going to stay the same. It's not always the same gas, it's not the same molecules, because we have evaporation and condensation happening at the same time. But this gas is going to exert a pressure, right? Because that's what gases do. So the pressure of this gas will be constant. So this is trying to look at this in a graph form. So here we have rate as a function of time. The rate of evaporation just stays the same. The rate of condensation starts at 0 because there's no gas to condense. And it gets higher with time because we're getting more and more gas. But when it reaches the same rate as the evaporation, now the number of gas particles is going to stay the same. And so they both become equal to each other. And this is the point at which we reach dynamic equilibrium. We have a process going in both directions, and the speed of that is the same. So what we call the vapor pressure is the pressure of the gas that's in dynamic equilibrium with its liquid. Now, we use the word vapor pressure when we were talking about gases, right? Gases collected over water. Remember those tricky guys? When you collect a gas over water, there's water vapor mixed in with the gas because this is happening. The water evaporates until it reaches this particular pressure, and that's called the vapor pressure. The vapor pressure is going to depend on the strength of the intermolecular forces. If we have weak forces, we're going to have a higher vapor pressure because the rate of evaporation will be larger. So here we have an equilibrium situation where we've got this hydrocarbon and it's evaporating and condensing, and so we've got some particles up there. If we disturb this system, if we raise the ceiling here, increasing the volume of the gas, what does that do to the concentration of the gas? It's the same number of particles in a greater volume, lower concentration, because there's more space, right? Okay, so if this becomes lower in concentration, then the rate of condensation is going to slow down for a while. And evaporation will continue at the same rate until they catch up to each other. And so we're going to end up with the same vapor pressure that we had over here. And then if we push down on the plunger and make this really small, now we've taken a large number of particles in a large volume, and now they're in a small volume, so the concentration is greater. That's going to make condensation happen faster. And so then the concentration here will go down until, again, they get to be equal, and the vapor pressure is the same. And that type of process is referred to as Le Chatelier's principle. If you take a system at dynamic equilibrium and you force a change on it, the equilibrium is going to shift around and try to restore the balance. Any questions? So what happens to the vapor pressure of a substance when its surface area is increased at constant temperature? This one's kind of tricky. Yeah, it does remain the same. So why is that? Well, let's draw two pictures. Okay, so here we have a rate of evaporation, we have a rate of condensation, right? Here, the rate of evaporation is going to be greater because there's more surface area. But eventually this is going to come to dynamic equilibrium, and the rate of condensation will also be greater, right? Because we'll get to that. We'll get to that vapor pressure, and at that point, these processes will be equal. So the vapor pressure is going to remain the same. What could we do to make the vapor pressure higher? We could change the temperature. So changing the surface area is going to affect the rate of condensation, because if you think about it, in order to condense, those gas particles have to hit the surface. So that's going to be partly dependent on the surface area. But if you increase the temperature, that's not going to affect the rate of condensation, but it'll increase the rate of evaporation. And so the vapor pressure will go up. So this is what we just talked about. The temperature, when the temperature of a liquid increases, its vapor pressure increases. It's because more of those particles have enough energy to escape, right? And so the rate of evaporation increases, whereas the rate of condensation remains the same. So sometimes a small change in the temperature can result in a large change in the vapor pressure. And this is just a graph showing vapor pressure as a function of temperature for several different substances. Water's over here. Here's ethylene glycol, that's in radiator fluid, coolant. Here we've got ethyl alcohol and diethyl ether. And we see with all of these that as you increase the temperature, the vapor pressure goes up. So the boiling point of a liquid is the temperature at which the liquid's vapor pressure equals the atmospheric pressure. So if we go back to this graph, we see that water, its vapor pressure increases, and it gets to 760, 1 atmosphere, at 100 degrees Celsius. That's its boiling point. And the reason it boils is that now molecules that are on the inside of the water have enough energy to get into the gas state. They don't have to wait until they get to the surface. And so they're going to form bubbles of gas within the liquid. And then those bubbles, of course, are less dense, and so they rise to the surface. And that's what we observe as boiling. Lots of big bubbles coming up, right? So it turns out the boiling point of liquids is going to depend on the atmospheric pressure. So what we call the normal boiling point is the temperature at which its vapor pressure equals 1 atmosphere. So that's the boiling point when the pressure is like normal, right? So for water, that's 100 degrees Celsius. So here's a graph of temperature versus amount of heat added. So if we take some water at 20 degrees Celsius and we add heat to it, it's going to get warmer, right? Until we get to the boiling point, and when we get to 100 degrees, it's going to start boiling. Once it starts boiling, it doesn't matter how much heat you put into it, the temperature will not go up. This is not something that it makes a lot of sense to the average person, right? Well, you're putting more heat in it, it should be getting hotter, right? I want my spaghetti to cook faster, so I'm going to get the water hotter. There's another train. Doesn't matter how long you boil that water, it's not going to get hotter until you boil away all the water, and then your pan's going to get really hot and start smoking and make a big mess. As long as the water, liquid water, is present, the temperature cannot go above the boiling point. Any questions about that? We're not going to do like calculations here, but if you're given a figure like this, you should be able to answer some questions. Like this one. It says estimate the boiling point of water at an external pressure of 200 torr. So what we want to do here is we want to find the pressure of 200 torr, and let's draw a line across. And we're looking for where does that intersect with the line for water. Well, that looks like it's close to 70, right? And we're not trying to trick you with these numbers. 66, it could be 66. Could it be 84? No, 84 is over here. 100's up there, 0's over here. So it's going to be 66 degrees. If we increase the pressure above 1 atmosphere, the boiling point of the water is going to be higher, which is why pressure cookers cook faster than just an open pot of water. And so, now we have instant pots, right? Instant pots are just modern pressure cookers. When you use the pressure cooker feature, as the water boils, it builds up pressure inside of the Instant Pot. And at higher pressures, the water will boil at higher temperatures.
For like H for water, for the specific problem,
Mm-hmm.
this water's boiling was 100.
Mm-hmm.
Why are we saying that it's below that? Like what gives us?
Well, here we're estimating the boiling point if the external pressure is 200 instead of 760.
Oh, okay, got it.
Yeah.
Understood.
So, anytime you boil something in water open to the atmosphere, it's going to be 100 degrees. And this is why frying food is faster than boiling food, because you can heat oil to a higher temperature, and a higher temperature will cook the food faster. Okay? So, anybody have any questions about that? There's an equation that describes the relationship between vapor pressure and temperature. If we go back and look at this, we can see these are not straight lines, are they? They are curves. But you can describe them with an equation. It's an exponential relationship, and you can rearrange that and end up with this. This is known as the Clausius-Clapeyron equation. The natural log of the vapor pressure is equal to negative heat of vaporization over R, the gas constant, times 1 over the temperature plus the natural log of a constant. So this is useful because if we graph natural log of the vapor pressure versus 1 over temperature, so the equation for a line is y equals mx plus b. So 1 over temperature is our x value. Natural log of p is our y value. And then the slope is this thing right here. So if you measure the boiling point, if you measure the vapor pressure at different temperatures, you can graph that data and calculate the heat of vaporization. So that's what they've done here. They've graphed the natural log of P versus 1 over temperature. Again, this has to be in Kelvin because we don't want to have a place where we have 1 over 0. And this is real data, and so it's not a perfect line, but you can see it's pretty good. And you can measure the slope of that line. The slope is equal to negative delta H over R. And so then you can solve for delta H and get it to find out what it is. So this is a question in the book. We can't really just do this in lecture, though, because we really need to be able to graph this, and there's a bunch of calculations that have to happen. But let's just talk about, well, how would you do that? So the natural log of the vapor pressure equals negative heat of vaporization over the gas constant times 1 over the temperature plus a constant. So I need to do some calculations on my data. I have my temperature in kelvins, but what I want is I want 1 over the temperature. So, that first one, I have to have 1 divided by 255. And so that's going to be 0.00392. And so you would do that for each of them. And instead of using the vapor pressure, I need the natural log of the vapor pressure. Let's squeeze it in over here, the natural log of the vapor pressure. So I'm going to take the natural log of 11.3, and that's going to be 2.4248. And then you graph that data, and you'd get a straight line. I can't remember what's on the next slide. No. I thought maybe I had the graph there. So you would graph that data, probably in Excel, and then you can determine the slope. And the slope equals negative delta H over R. So then rearranging that, you get delta H is equal to negative R times the slope. These are the sorts of things we do a lot in Chem 1B, if you're curious. We can also take that equation and express it as a 2-point form, because 2 points define a line. So we're not going to do a bunch of graphing and stuff, but we should be able to use this equation. So this is the 2-point form of the Clausius-Clapeyron equation. So here we have 4 variables, 2 pressures and 2 temperatures. And if we know 3 of those, we can calculate the 4th. Or if we know all 4 of these, then we can calculate delta H. I guess it just has the answers sticking right out there. Okay, so this is kind of a difficult problem, but we can do it. So propane has a normal boiling point of negative 42 degrees Celsius and a heat of vaporization of 19.04 kilojoules per mole. What's the vapor pressure at 25 degrees Celsius? So we're looking for vapor pressure. So we're going to use this equation, which we were not expected to memorize. So this is our delta H, right? They gave that to us. And we've got 2 temperatures here. Well, let's call the first one temperature 1. So temperature 1 is negative 42 degrees Celsius, but we have to use Kelvin, right? So 273.15 plus negative 42 is 231.15 Kelvin. Temperature 2 is 25 degrees Celsius, which is 298.0 Kelvin. We want the vapor pressure that goes with temperature 2. So we're looking for pressure 2. But they didn't tell us what pressure 1 was.
Would it be at a constant at all?
What does normal boiling point mean?
100 Celsius?
Well, for water it would be.
Oh.
But remember, boiling point depends on pressure. So the normal boiling point is when the pressure is normal. What's normal pressure? 1 atmosphere, or 760 millimeters of mercury, or 760 torr. The answer's in torr, so I'm going to use torr here. So pressure 1 is 760 torr, and you have to get that from the word normal. It doesn't come out and tell you that. So now we can plug these things in. We've got natural log of P2 over P1. P1 is 760 torr. And that's equal to negative delta H, 19.04 kilojoules per mole. No, this is not going to work. Divided by R. Here we've got energy, and so we're using the energy version of R, which is 8.314 joules per mole Kelvin. And then we've got 1 over T2, which is 298.0 Kelvin, minus 1 over T1, which is 231.15 Kelvin. And then let's look at our units before we do any calculating. I've got moles and moles. Those are going to cancel out. And the kelvins are going to cancel out, even though it kind of doesn't look like they will. But are kilojoules going to cancel joules? No. So this is one of those places where we need to use our little shortcut trick there and do times 10 to the third joules per mole. This is the kind of an equation that if you have a TI-36X Pro with a number solver on it, you can just type the whole thing in like this and put in X for P, and it'll solve it for you. But most people don't have one of those. So I'm going to find the value of all of this first. So I've got negative 19.04 times 10 to the third divided by 8.314 times, and I'm going to use parentheses, 1 divided by 298 minus 1 divided by 231.15, close the parentheses and press equals. We're not doing any least common denominators for the fractions. 2.22253. No, that's probably good enough. And that's going to equal natural log of P2 divided by 760 torr. How do we undo natural log? The anti-log, right? So the anti-log of that is e to the x. So I'm going to do e to the x of both sides, and so these guys cancel each other out, and I get P2 divided by 760 torr is equal to e to the 2.22 blah 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 which is 9.23068. And so then I'd have to multiply that by 760. And I get, oh, it's close. So that would be 7.02 times 10 to the third torr. Book says the answer is 7.04. Is that a deal breaker? What do we know about the last significant figure? There's some uncertainty there. So this is a little bit different in that uncertain place, and so it's okay. Any questions? I will show you how to put it in there. Yeah, just ask me during lab.
Because I tried it and I couldn't get any like more numbers than I was like, oh.
Yeah, same here.
Okay, so that might be an issue, but yeah. What if we take our sealed container and we heat it? So as the temperature rises, the pressure is going to rise also, meaning that the gas gets more dense, the liquid becomes less dense, and at some point, they become the same thing. They become a supercritical fluid. So here we have a gas and a liquid, and as we increase the temperature, the gas becomes more dense, the liquid becomes less dense, and above the critical temperature, you just have a single state. It's not a gas or a liquid. So the critical temperature is the temperature above which a supercritical fluid forms. And the pressure at that temperature would be called the supercritical pressure. Supercritical fluids are really useful solvents. This is one of the ways that coffee can be decaffeinated. You can use supercritical CO2, and that will dissolve the caffeine, but it doesn't take out a lot of the stuff that makes the coffee still taste good, if you like coffee. And leaves no harmful residue. Because what happens at the end? The CO2 evaporates, right? Nothing left behind. Pretty cool.